What J tells you is this. The chart is set up so that you can do these electron configurations very easily. This is your s orbitals. That's your d orbitals, and this is your p orbitals. If you use your chart, your periodic table, from left to right, and that's why he takes helium and he sticks him over here, okay? Because helium is just filling an s orbital. The reason helium's over here is because these are the noble gases. And the noble gases are called that because they're gassed at room temperature, but they're noble because they don't like to interact with anybody else. And the reason they don't like to interact with anybody else is because they already have the ideal electron configuration, so they're happy. Everybody's at ground state, everybody's filled, they're happy. They're hermits. They're like, and everybody else wants to be them. Okay? And that's what chemical reactions are about, is everybody trying to be them. That's really what it gets down to. So when you do it with that information, and he shows you that on page 106, you see the s orbitals are over there, the d orbitals are here, the p orbitals are here. Down here you have the f orbitals. Okay, but we're not going to deal with those. Thank you, Jesus. So now when you do it, you can actually use the chart. So let's do an example problem. Let's see. Over on page 108, it says, do the electron configuration for oxygen. So instead of being tortured like I would have had to, where you just had to have memorized where you went down back from the, you went to 4S and then you went to 3D, and you just had to have all that memorized, he gives you a way that you can use the chart. Let's do oxygen. So what you do is you go left to right. You go one, and you just go left to right, top to bottom, until you get to wherever you're going. So I go 1s2. So I fill the 1s because I got to get down here to the second level, don't I? Now I go 2s2. So I'm going to write down 2s2. And now I go 2p, 1, 2, 3, 4. 2p4. There's oxygen. You just use the chart. The next one is rubidium. And rubidium, down there, 37. Okay, so we're going to go across again. 1s2. 1s2. I'm just going to show you where rubidium is. It's over here. Okay, so now we're going to go 2s2. We're going to go all the way across the second level, aren't we? 2s2, 2p6. We're going to go to the third level. 3s2. Got to go over here. 3p6. Got to go back over here. 4s2. Now, when you get to the d orbital, even though it's on the fourth level, you subtract one from the energy level. So this is 3d10. Okay? So that's going to be 3d10. You're back to 4 when you get back to here. So this is 4p6. 4p6. Like I said, I had to have all that memorized. You can look at your chart and do it. And then you come back down here, and it's 5s1. So you add your 5s1, which is a really ugly 5, but anyway, 5s1, and you're done. There's rubidium. So you just use the chart. You just go across the chart and you read it. When you get to the d orbitals, you're going to just subtract 1 from whatever the energy orbital is. But remember, when you get back over here to p, you're going back up to what that energy level was over there. Is everybody okay on that? So let's see. Then he says, chemists are notoriously lazy. I'm with him, man. And he says, so they came up with an abbreviated version. And what you do on the abbreviated version, let's say we were doing rubidium again. Instead of having all that craziness, wherever rubidium is, and it's in 5, you go to the noble gas and the one above it. So we go to the noble gas in 4, which is krypton. So we would go and put it in brackets. If you don't put it in brackets, it's not right. So you would go, I'm sorry, it shouldn't be krypton, it's kryptonite, right? Is it kryptonite or krypton? Hang on. Yeah, I'm thinking Superman too. You guys too? It's krypton. I was right in the first place, sorry. It's Superman that has a problem with kryptonite. Okay, so it'd be krypton, and then you'd go 5s1, and this is the abbreviated version of this.
Wow.
Oh, yes. Yes, praise Jesus. This is great, right? Woohoo! So, yay!
I know.
So,
You're going, what?
yeah.
You're like, abbreviated that.
Well, that's why I wanted to show it to you. Make sure that you put it in the brackets. So arsenic, and it shows us there that he wants us to do arsenic. So arsenic is here, okay? Arsenic is right here, which is in 4. So which noble gas are we going to use if we need to do arsenic that's in energy level 4? Good, we're going to go to energy level 3, and it's going to be argon. And so we would put that, and then we start from there. So we go back over there, and we go 4s2, we get to 3d10, we go back to 4p, and we go 1, 2, 3. And there's our abbreviated version. How are we doing? We okay?
Yeah.
It's easier to show this to you than to try to do it in the book, although I thought he did a pretty good job. But it's easy when you see it, isn't it? And I'd have paid for this information in college. Literally, when we had a test on this, we're sitting there adding up electrons, and we just had to know when to jump from 4s to 3d, and then back to 4p, and then 5s, and then 4d, and then back to 5p. Nobody showed us it was on the chart. No, you're laughing. It's not funny. And I think it's because, and I should do my little rap right here, but I'll tell you why. I think it's because chemistry is a weed-out course at the universities. Chemistry, calculus, and physics are used as weed-out courses at the university level. And I went to 2 universities. I went to Auburn University and the University of Florida. The reason I say that is because they're trying to weed out all the pre-meds, pre-vets, pre-pharmacy, all your professional school students. They're trying to weed them out. And so as far as I can tell, they just do the worst job they can at teaching those classes because they're trying to see who can survive. And if they can kill you, then you're less to deal with. And so they jam you in a classroom with 1,000 other people and see if you can figure it out. And actually, when I went to Auburn, back then, my first 2, Dr. Quagliano and Dr. Valerino, couldn't speak English. They were Italian from Italy, and you could not understand them. After that, they actually passed a law that they had to be fluent in English to be able to teach at universities in the United States. But it did not pass until after I was through these people. Couldn't understand most of what they were saying. But they didn't care because these were weed-out courses. Now, part of the reason that I say that is because my husband did the 20-year plan in college, and after we got married, he went at night when he'd work all day and go to school at night. And he went to several, at the time, what would now be state colleges. They were community colleges. He got some great teachers. And I said to him, how is it that you got such great teachers? And I went to 2 major universities and I got such lousy teachers. And we talked to some people and found out that it's because the teachers, the professors that are hired at the universities are hired for their research. And they're hired for their research, so they're not hired for their teaching ability. And they teach as a sidebar to their research, and the university wants the money from their research. Whereas a teacher that's at the state colleges, that's all they do, is teach. So you've got a better chance of getting a better education on your weed-out courses from your state colleges. Now, I had one student when I told a group of students that in chemistry up in Orlando, and she wanted to be in med school, and she goes, well, they told me that I had to go to a university to take my chemistries or they wouldn't accept it at the med school. And I smiled at her, homeschool student, I smiled at her and I said, you need to contact the medical schools and see if that's true, because I don't think that's true. I said, I think they're trying to sell you courses, because her counselor told her that at the University of Central Florida. And she came back the next week and she said, I called 3 medical schools and they don't care where I take my chemistry. I said, that's right, they don't. Which what that means is this, my beloved friends and Christian brothers and sisters in the Lord, if you are going to go to University of Florida or Auburn University or Florida State or someplace like that, and you have to take chemistry, physics, or calculus, I would seriously suggest you choose to go to Santa Fe while you're taking your other classes at Florida. Go to Santa Fe for those classes. Go to whatever your state college is that's local to your university for those classes. You will get a better education on those classes at the state college in general than you will at the universities for exactly that reason. I had the one chemistry professor, have I told you guys about Dr. Ward yet? Oh, all chemistry students have to hear about Dr. Ward. I had one chemistry professor at Auburn University, and we have time. I had one chemistry professor at Auburn University that I loved. I'm sure he is gone now. His name was Dr. Ward. He was a fossil back then, okay? He was like ancient, and he always wore the same thing. Black pants, long sleeve black shirt. Never saw him in anything else, okay, ever. And he comes wandering in, and this is your second chemistry. He's not the first term of chemistry. As a matter of fact, he's your sophomore chemistry, so he's second year chemistry. So you sit down, you're still in one of these huge rooms, and you come in and you sit down, and we're all waiting for the professor. And this old man creeps in with a children's book under his arm. And he comes in like this, and we're all thinking the man's in the wrong place, you know? Comes in, sets his children's book down, and he literally starts to read us Aesop's Fables. He always started his class this way. And he starts to read us the story of the tortoise and the hare. And we're all, by this time, we're giggling and we're bumping each other going, this old man's in the wrong place. And then he finishes reading the tortoise and the hare. Literally spends like 10 minutes reading us the tortoise and the hare. He looks at us with this very Yoda-like look on his face, okay, with his glasses down here. He looks at us and he goes, be the tortoise. And at that point, you should have been afraid, okay? Because he was really making a point. And Dr. Ward was a tremendous chemistry professor. And I loved him. And I would literally follow him back to his office. After class, I would walk him back to his office for about 2 weeks before an exam. And I would live on a desk he was in the bottom of the chemistry building. And there was an old desk shoved out in the hallway outside of his office. And I would live on the desk outside of his office and study. And then if I had questions, he was so nice. I would just go in and ask him my questions, and he would help me. And I'd go back out and I'd park, and I'd camp on this desk for about 2 weeks before an exam. Well, I thought, he was great. As a matter of fact, I worked my whole schedule around him the next term because I wanted to make sure I had Dr. Ward for any class I had. And as I'm walking him back one day, we got to be pretty good friends. And I'm walking him back, and I said, why is it that you're such a good chemistry teacher and all the rest of them are so bad? You know me, I would ask that kind of question, especially when I was like 19. And he goes, I can answer that question. Tenure. He goes, I've been here so long they can't get rid of me. and apparently he came with some pretty good research. We also got to be good enough friends that Dr. Ward he rode a bike everywhere. Now this man smoked, so he was not a health nut, okay? He smoked, but he wouldn't own a car. He rode a bike everywhere. So one day, I felt like I knew him well enough. I said, Dr. Ward, why won't you own a car? And now get this. Dr. Ward was the man that developed antifreeze for Standard Oil. He's the guy that made antifreeze. That's how old he was. And they never paid him for it. And so he was so angry at the whole industry, he refused to own a car. He refused to get in a car. He was wild, okay? That was Dr. Ward. I loved him dearly. He was just great. And I want you to know why else I love him. When I left Auburn, I finished my chemistries there. I went to the University of Florida, my home state. When I tried to get help from a professor in chemistry, they wouldn't even speak to me. You are an undergraduate student. We don't speak to undergraduate students. You make an appointment with my grad student. I go, what do you mean you don't speak to undergraduate students? He goes, I had several of them. We only deal with graduate students. I go, where do you think they come from? They don't just pop up. We start as undergrads, You know me, I was not always a Christian, and I was a bad person. My mouth gets me in trouble. But anyway, but the point is I could never get to a professor to get help in any of the chemistry departments at the University of Florida. And actually even at Auburn, Dr. Ward was special. He was very special. And so I sure hope he was a Christian. Anyway, all right, let's just finish this up real quick. Let's see. So valence electrons are on page 109. Valence electrons are the outermost electrons, and they're very, very important because they show how the chemistry of a particular atom is going to be, how it will respond. Why? Well, if you think about it, when the atoms come together, what comes together? The valence electrons. And remember, because they are negatively charged, they're going to repulse one another. So the only interaction is going to be with those outsidemost electrons, which are the valence electrons. So valence electrons are extremely important because they tell you the actual chemistry of any particular element and how they're going to get together. And the chart is actually, and I'll keep calling it a chart because to me it's the periodic chart. Everybody else calls it the periodic table, but it was called the chart when I was in school. And so the chart is actually set up to show you those periodic properties, and you'll have a test on that at a point. But the valence electrons are the outermost electrons. They're the first to interact with others, and the elements are grouped in columns with similar chemistries. So everybody in this column has similar chemistry. They all have one electron hanging out in the outer level, and if they can ditch that one electron, then they'll look like a noble gas, and everybody wants to be a noble gas. And so everybody over here is just going to ditch the outermost electron. That's what they all have in common. Now that's why helium's over here. And actually, you're going to be learning soon that this side of the chart are metals and this side is nonmetals. Well, hydrogen's a nonmetal. But because it has the one electron, and if it can ditch it, then it'll have a full electron configuration by having none. That's why it's over here. Okay? But let's say everybody in here, in group 2, they all have 2 electrons in the valence. They want to ditch 2 electrons. If they can ditch 2 electrons, they'll look like a noble gas. And that's what they want to do. And then when you get over here, and he makes a point that it says these are in the A columns, okay? The 3A, well, they have 3 valence electrons. Now, it's easiest for them to ditch the 3 to get to the noble gas, isn't it? But in general, metals give away electrons. You're going to be learning this soon, and nonmetals will take electrons. And so boron will actually try to grab 5, which is crazy, and so he won't play with boron very much. These guys will actually give away 3 electrons so that they can look like they have, they'll ditch 3 valence electrons so that they'll have a valence that'll look like the electron configuration of a noble gas. When you get over, let's say, to oxygen. Well, now oxygen's in group 6. It's easier for oxygen to grab 2 electrons than it is to ditch 6, right? So oxygen is going to grab 2 electrons. If it can grab 2 electrons, then it's going to have the noble configuration, the electron configuration of the noble gas neon. And so that's what it's going to try to do. So it's going to end up with a -2 charge because it's going to grab 2 electrons if it can. Do you just see a general pattern here? So that's why we see when he asks the question at the bottom of the page, on page 109, which of the following elements have similar chemical properties? Well, potassium's over in group 1. SC, I can't remember where it is. There it is. It's over here, number 21. Mg is magnesium over there. Chlorine's way over here. And then Sr and silicon. Silicon, well, let's see, where's Sr? Sr, there. These 2 are in the same group, and therefore they will have similar chemical characteristics because they're in the same group. Okay? Any of you Star Trek fans? Okay. Remember in Star Trek, the one with the Horta? I don't know if you're going to, that's really old. That's an old Star Trek. It was a silicone-based life form. Do you know why they expected to find a silicone-based life form? Because we are carbon-based life forms. So they thought that if another life form existed, maybe it would be a silicone-based life form. And therefore, they did a Star Trek with the Horta, which was a silicone-based life form. Okay. Just a little trivia there. Okay. How we doing? We can do this, can't we? Yeah. Praise Jesus, we can. All right. Have a great week, and we'll finish this chapter next week. And you can spear Clay dough too.